Okay, thank you very much for inviting me to this wonderful school, and yeah, it's my great pleasure to give a lecture here. In this course, I'd like to talk about some relation between quantum information theory, especially quantum entanglement measures and its application in quantum field theory. So let me start with some introduction. So basically, in quantum information theory, so typically, the question to be asked is as follows. So in quantum information theory, so I will write it as a QIT. So basically, quantum information concerns with a state convergence. So namely, so you have two states, quantum states, say psi, and you're interested in how you can transform this state psi to another state phi by some given operation called lambda. So yeah, I do not specify what lambda is now, but okay, basically the question is that, okay, you have some set of operations you are allowed to perform between two states, and if you act some operation on the initial state, and you end up in some states. But the question is that, so what operation? So what operation you can have allowed in quantum information theory? So this is one basic question in QIT. And another question is that, okay, this is very related to the first question. So when psi can be transformed to another state. Okay, so given two states, psi and phi, so when can you transform psi to phi under the operation you are allowed to perform? So this is the basic question in quantum information theory. And so this question is actually related to the ordering. So ordering of quantum states. And okay, so very roughly speaking, okay. So you have a space. So you have space of quantum states. And you have, this is very dynamical question. So you have 2 points, psi and phi. And the question is, so what? Yeah. So when can you transform the initial state to the other by under the allowed operation lambda? So we want to answer this question in the set of quantum information. But why should we care about such a question? So I'd like to basically I'd like to review the basics of quantum information and answer to this question first in the first part of my talk. And now, in the second, I'd like to point out that in quantum field theory, we have a similar question. Okay, so basically, so now we have a space of quantum field theories. So namely, so each point corresponds to some QFT. So you can imagine that so this space is parameterized by some coupling constants. Okay, suppose you have free scalar theory, and then the mass parameter is a one direction in the space of quantum field theories. And now, so the very basic question is that under, say, the renormalization group flow, so when a given theory, so say T1, can flow to another theory, T2. So this is very similar question as in quantum information theory. So more precisely, so under RG flow, so when, say, one theory T1 flows to another theory T2, so this is also the problem of ordering. So ordering the quantum field series. So this type of problem is called, basically formalized as a C theorem. And there are many examples of C theorems. And I'd like to talk about the relation between, say, some information theoretic aspect of C theorem in this talk. Okay, so this is my motivation. And okay, so now let me very briefly explain what the quantum information theory is. So as I briefly mentioned, that basically quantum information theory concerns with the state conversion. So given one state, given a pair of states, so when can you map one state to the other under an allowed operation? So we need to make it more precise. So what's the operation is in the context of QIT. So basically, so in QIT, psi, so every state, so the states are some, of course, quantum states, quantum. And now, so the operation lambda is usually restricted to so-called LOCC. And LO and CC means that local operation and the classical communication. So basically, so you can perform some unitary transformation locally. So suppose you have a bipartite system. So here, so there is some system A, and here, so there is some system B. So Alice and Bob, and they are separated. So they can only perform local operation on each side. Say, so Alice performs some unitary transformation on her side, and Bob also transforms some unitary transformation, UB, and they can also communicate classically. Say, so they can, they measure, they perform some operation on their system, and they get some output, and then they can tell, say, suppose Alice tell her result to Bob by, say, telephone or sending email. Anyway, so this is the classical communication. So this is the basic setup in quantum information theory. So these are local. So this is local operation. Okay, so of course, okay, she can perform some projective measurement, some measurements, so which is not necessarily the unitary. So this UA can be some, say, some local operation. So this is a basic setup, but this is very vague, very ambiguous definition of LOCC. So I will make it more precise later. So there is a more mathematically rigorous definition. So actually, LOCC is not so easy to understand, and there is a family of LOCC operations known in QIT. But I will use more easier definition, easier operation we can use in QIT later. But okay, at this moment, just suppose that you have some operation, and you are concerned with state transformation. So Then you have some operation, and you want to perform some operation on quantum states. So before before answering to the dynamical question, so let's start with the classification of quantum states. Classification. But okay, I will only talk about the pure bipartite system. Okay. So basically, I only talk about pure bipartite system. So it means that okay, you assume that the Hilbert space can be tensor factorized as follows. So this is very, of course, strong constraint. But anyway, so let's suppose that, okay, in this case, we call the system is bipartite. So you have two systems. Of course, you can consider multipartite systems. But now, for simplicity, I assume that the system is bipartite. And when I say the system is pure, then, so I will write the density matrix of H by, say, rho, and suppose that you have some vector quantum states belongs to the total system, then you have density matrix, and density matrix is called pure. So when it takes this form, so basically you have only one state psi, and that's it. And if the density matrix or the system is mixed, then you have some linear combination of states. So if state is mixed, so then rho would take this form. Okay, I think this is very well-known fact, so I do not have to explain it. Okay, anyway, so I assume that the system is pure, so this is pure. So this is pure. Okay, maybe I should write it in color. So this is pure, and this is bipartite. Okay, now so I want to classify pure bipartite quantum states. And this is actually very easy. So first, I will give you very rough classification. So let's first define separable states. So separable state is very simple because, okay, when psi can be written in this form, okay, with psi A and psi B, of course they belongs to the Hilbert space of A and the Hilbert space of B respectively. So then the state is called separable. Okay, this is very simple form. Okay, now you imagine that you have two spin systems, A and B, up and down, for example. And if your quantum states, if you can find some nice states, psi A and psi B, such that psi can be written in this form, then you say that the psi is separable. And right. And okay, there is another class of states. So that is called entangled states. So the definition of entangled state is, by definition, not separable state, non-separable states. So you cannot find any psi A and psi B, which gives you this form. So entangled state, okay, the separable state is very special states in quantum states. And there are many examples of entangled states. So let me give you one basic example. So this is called Bell pair or EPL pair. Okay, most states are completely entangled, but okay, in the case of two-spin systems, this state is the simplest. So one of the Bell state is defined as follows. Okay, now, I suppose that the system takes two states, 0 and 1. Then Bell pair state is given by this. So you have 0, 1 plus 1, 0. And if you try to find psi A and psi B such that psi can be decomposed in this form, so you won't, it fails actually. Yeah. If you haven't tried, then I recommend you to do this program by yourself. Anyway, so there is, okay, this state cannot be written in this form for any psi A and psi B. So this is easy exercise, of course. And so, okay, so basically, so this is a rough classification of the pure bipartite states. But okay, we want to refine it, this classification more precisely. So to this end, so we need to find some canonical form of quantum states. So it is called Schmidt decomposition. So Schmidt decomposition is basically some canonical form of a bipartite quantum state. Okay, in general, any quantum states, okay, any bipartite quantum states can be written in this form. So I and J. Okay, you have some coefficients, Cij, and you have some orthonormal basis for the Hilbert space of A and Hilbert space of B. So these are orthonormal bases. And you have, this is complex coefficients. So this is a general form. And of course, I assume that IA and JB span the orthonormal basis. But okay, so this is too general, but we can make it into canonical form as follows. So basically by changing the orthonormal basis by using unitary transformation. So, so by changing the orthonormal basis, say, okay, you act some unitary transformation on, on the basis A, like this. Okay, and yeah, similarly, so you act some unitary transformation for also on the basis of B, and these are unitaries. So U and V are unitaries. Then, roughly speaking, you can diagonalize the complex matrix Cij. So, of course, Cij is not, it's a rectangular matrix. So, basically Cij, okay, I and j runs in different dimensions. So, this is dA by dB rectangular matrix. Complex matrix. Sorry, so dA and dB are dimensions of Hilbert space A and B, respectively. So these are dimensions. So Cij, roughly, so this is length dB, and this is length dA. Sorry, opposite. I think dA times dB. Okay. Okay, so this is rectangular. But even for such a complex matrix, you can diagonalize using so-called singular value decomposition. Singular value decomposition. Okay, this is just a linear algebra. So using singular value decomposition, so Cij becomes, okay, I'm very sloppy about notation, so I don't remember which unitaries I use, but okay, roughly, so you can diagonalize Cij by two unitaries, and lambda is a kind of diagonal matrix, but of course, so Cij is rectangular, so you would get some partially diagonal matrix, lambda d and 0. So this is, okay, suppose that the dA is greater than dB. So suppose dA is greater than dB. So then, so you have a diagonal matrix, so dB by dB diagonal matrix here. Well, but you still have to have a 0 vectors on the rest to make it rectangular. So this is called singular value decomposition. And a nice thing is that, okay, since you can use two unitaries, two unitary transformations, so you can make lambda be lambda i's are non-negative. So you can make them to be non-negative number, non-negative real number. And if you normalize the state, then the sum of the eigenvalues is just 1. And okay, so here, okay, I runs from dA, the minimum of dA and dB. Okay, is it clear? Okay, so I showed you that, okay, the case when dA is greater than dB, but you can, of course, change their roles. So basically, so the eigenvalue, okay, this index of lambda runs from 1 to the minimum of dA and dB. So this comes from normalization. And of course, you can further order this vector lambda as follows. So, okay, I will order these coefficients in the descending way. So lambda minimum. So of course you can change the label of this vector. So in this way. So this is the canonical form of the quantum state. And okay, so I will use I will define a vector, so lambda psi, so whose entry is I didn't have a superscript psi, but now I put superscript psi to indicate that this eigenvalue is for state psi. So you can define some vector, a vector of the eigenvalues. Okay, so basically, so lambda i's are called Schmidt coefficient, and so I'd like to call this vector as a Schmidt vector. So now, we have a canonical form of quantum states. So we can talk about the more refined classification of quantum states. So basically, given Schmidt vector of some quantum states, now you can talk about the order of the vectors. So now you can introduce some order. So now we want to introduce order between quantum states. Using this Schmidt vector. And actually, this is possible, but so the reason why I use order is that it's not literally the order. You can only introduce a partial order. So now you can introduce a partial order. Map from psi to phi.
I to psi. We are not considering the unitary, dynamical. So that lambda map can be linear to unitary.
So are you asking that the lambda is unitary or not?
Lambda map may not be unitary.
The lambda is not necessarily unitary. Yeah. In general, it's not unitary. Yeah.
And other thing is in the space of QFT is considered. So that you are that space only consists of the QFTs connected by RG.
I only consider that the series between connected by RG flows. Yeah, in that figure, yes. Well, basically, the theories I'm concerned with is CFTs, and I'm interested in the RG flow between two CFTs. But more generally, you can of course consider the RG flow between any quantum field series. Yeah. Okay. Do you have any question? Oh, yeah. You're asking that the Hilbert space is, so when Hilbert space is real, of course you can do the same thing for real spaces. Yeah. It's just okay. So now, of course, the vector is now complex in quantum mechanics, but if it were real, then you would do the same thing, like Schmidt decomposition for the real vectors as well. Yeah. Oh, maybe you were worried about the positivity of the eigenvalue. I don't know. Yeah, maybe there must be some operations, some counterpart of singular value decomposition for real matrix, but I don't know much about it. Sorry. Okay, so so far, okay, so what we have done is that, so given a quantum state, so we can make it in a canonical form, and basically any quantum states, of course, bipartite states, can be written in this form. So it is completely characterized by the shemitah vector. So this is the eigenvalue. Roughly speaking, this is the eigenvalue of the quantum states. So given the shemitah vector, so you completely specify the quantum bipartite states. And now we want to introduce a kind of order between quantum states using this form. So, but you can only introduce a partial order, so not complete order. Okay, I will explain why. Okay, so first, so we will introduce an order between two vectors. So the partial order will be written using this symbol. And so suppose you have two vectors, x and y. Then you introduce a partial order. So when they satisfies the following relation. So you first, so by the way, so x1, okay, so these, okay, of course, yeah, I order these eigenvalues in the descending order. Okay, for the two vectors with descending eigenvalues, then I introduce a partial order as follows. The sum of the first k eigenvalues of x is less than that's for y, and for any k. So this is the definition of the partial order between two vectors. So let me give you one simple example of the partial order example. So if all the eigenvalues are the same, then so such a uniform distribution is actually the least, okay. Yeah, so any vector, okay, so I think I need some name. So in this case, so we say that, okay, x is majorized by y. So this is known as the majorization of the vectors. So I say that it's okay if x and y satisfy this relation, then x is majorized by y. And the example, the simple example is that, okay, the uniform eigenvalue distribution is majorized by any vectors actually. But okay, for simplicity, I will give you this example. For yes. So you're asking that okay, yeah, good question. So okay, you're asking the Schmidt decomposition or quantum states. Yeah, okay, more precisely, okay, so these vectors need not to be ordered in this way, so in the descending way. So more precisely, okay, so for simplicity, I use this definition, but more precisely, okay, so let's remove these conditions. So then, so you can define a partial order in this way. So xi with superscript with down arrow means that you order the eigenvalues in the descending way. So this is more precise definition. Yeah. So the example of the partial ordering for the vectors is as follows. Okay, so the uniform distribution is modularized by, say, the vector on the right hand side, and similarly, so this vector, so this vector also modularized by this one, and you can repeat the same game, and you end up with 1 0 0 0. So the vector with 1 0 0 0 0 is, in some sense, it is most strongest vector in this order. So it is in the rightmost side, in the rightmost. But on the other hand, the uniform distribution given by n 1 over n, 1 over n, is in the leftmost in this order. Yes.
Question: if the sum of every elements in the vectors is the same.
I'm sorry. Oh yeah. Thanks. Yeah, thanks. Yeah. That's a good point. Yes. Sorry. Yeah. Yes. I assume that the sum of the eigenvalues are the same. Okay, n is the dimension of the vector. Okay, so these are two vectors in Rn. Yes, thank you. Yes. Okay. So now, so this is a simple examples, but okay. The reason why it is called partial order is that so there are vectors that cannot be compared. Okay. So the reason why partial is that okay. So there are vectors which cannot be compared. So namely, okay, so there are some vectors, so which is, okay, suppose that you have x and y, and x is not modulated by y, and also y is not also modularized by x. So there are such examples, so actually many examples. And for instance, so this is also example. X is, suppose, three-dimensional vector. X is this form, and y is this form. And then, so you can check that, okay, so suppose that, okay, the first entry of x is greater than the first entry of y. So okay, so when k is equal to 1, so you want to compare x1 and y1. x1 is 1/2, which is greater than 2/5. So this is y1. So you would expect that y is modularized by x, but if you go to k equal 2, then you need to sum. So x1 plus x2. x1 plus x2 is 3/4, and y1 plus y2 is 4/5, and 4/5 is larger than 3/4. So, no, opposite. So this pair cannot be compared, so cannot be ordered. Is it clear? Maybe this is too simple. But yes? So, sorry, could you repeat your question again?
What I'm trying to say is there a particular reason that we chose the ordering to be like applicable for all k's? We could have in principle just chosen the ordering to be applicable for k equals 1, in which case it should always be applicable, right?
Well, yeah, so this ordering is particularly nice when you classify in entangled states, as I will show you. Yeah, so this is particular ordering of the vectors, yes. So there are many orderings. So as you say, so you can just compare the first argument, first entries of the vectors, and you can introduce such an order. But such an ordering is not so useful in classifying the quantum states. So when you talk about entanglement entropy, quantum entanglement. Okay, so the reason why I introduced such a partial order is that so this ordering is actually turns out to be very useful. So when you try to answer the first question, so maybe second question in quantum inference theory. So when okay, so let me go back to. So now let me go back to the original question. So okay, so we asked that okay, so when a state actually, I only talk about pure bipartite quantum state. So when state psi can be transformed to another state, by LOCC. So this is the QIT problem. So we'd like to answer. So but okay, so we introduced a partial order between two quantum states. So but we haven't specified what you can do by LOCC. So let me give you quickly. So what's the LOCC is. So, okay, I don't want to talk about the full details of LOCC, but I just give you some rough idea of LOCC. Okay, LOCC is actually a subclass of so-called separable operation. So this is called separable operation. And separable operation is mathematically easier to understand. So let me first tell you about what SEP is. So lambda, so when lambda is SEP, so then it maps a given density matrix to a sum of density operators of this form. So AM and BM are, so these are unitary, so local unitary operators. Sorry, not necessarily unitary, sorry. So AM and BM are some operators satisfying this condition. This is one for system A, and the sum of BM dagger and BM is identity operator on Hilbert space B. So they satisfy this condition. So this is called the separable operation. So it is clear that, okay, this operation implements the local operation because, okay, so the AM tensor BM, so A tensor B is a local operation. So it acts on locally on each subsystems A and B. And this sum, okay, so but the question is how you implement classical communication. Actually, so yeah, you can show that, okay, any reasonable LOCC can be written in this form. So I don't want to give you more detail, but yeah. So this summation basically corresponds to the classical communication. Basically, so Alice performs some measurement and she performs some unitary local transformation and she sends her results to Bob, and then depending on the results, so Bob also performs some another transformation, and such a operation can be written, always can be written in this form. So the SEP is larger class of the operation than LOCC. So I will use the SEP instead of LOCC for simplicity. And if you are interested in yes? Okay, yeah. When you just define SEP, then rho can be mixed. Yeah, but I will only consider pure states.
So if you remove the classical communication part, then the sum over M could actually be just one, and A and B are unitary.
Wow, yeah, you are right, yeah.
Okay.
Yeah, if you remove this one, yes, yeah.
Okay.
Yeah, so there are vast literature studying the operations in quantum information theory. So, yeah, it's too much for me. So, I just skip the detail of LOCC classification. So for simplicity, you just consider these types of operation. Okay, any question? Yes.
And for the separable state, we will choose the position representation or some other representation.
I'm sorry, could you say again?
As for the separable
Uh-huh.
operation, we will need to choose the position representation.
Position means you mean in quantum mechanics? Position.
Maybe the separable maybe depends on the representation, the choice of the representation. Momentum representation.
Oh, I see. Yeah. Basically, yeah. So the separable depends on, okay, the meaning of separable depends on how you decompose your hyperspace. So I only imagine that the systems are spatially separated, but of course you can decompose your hyperspace in momentum space. So in that case, you can define similar separable operation acting on momentum space. Yeah.
Why do you call it classical?
Classical communication?
Yes.
Because it's not quantum. Yeah. But basically, yeah, you just send your information respecting causality, for example. Okay, or yeah, just a classical communication. Yeah, classical communication means you can send your information after you get some output after the measurement.
But from this definition,
Oh, this definition?
yeah.
Oh, yeah. This is, yeah. Okay, this separable operation includes LOCC, but of course there are exceptions. So, yeah. But as long as you consider the pure quantum states, so they act similarly. So, yeah. So, okay. Yeah, I don't want to go into the details. So, if you are interested in, yeah, please ask me later, personally. Yeah, how much time do I have? 30 minutes? About 30 minutes? 25? 30 minutes? Okay. Okay, so this is the operation we will use, and so now, I'd like to give you very beautiful result answering to our question. So this is called Nielsen's majorization theorem. Okay, so this Nielsen is not, that's Nielsen, well-known Nielsen to us, but this is Michael Nielsen. So Michael Nielsen in quantum information theory. So he has a textbook, so Nielsen Chuan. So this is Michael Nielsen. Okay, so he proved the following theorem. So for bipartite pure states, psi and phi, then psi is transformed to phi if and only if, okay, under LCC, or more generally separable operation, if and only if the Schmidt vector, so lambda psi, is majorized by the Schmidt vector for phi. So namely, so psi can be transformed to phi under sep. Okay, yeah, I'm writing the same thing, but okay. So this is the theorem. Okay, so this is very clear-cut answer. Oh, it's gone again? Okay. Okay, so now, so this is clear-cut answer to our question. So given the two bipartite pure states, psi and phi, so psi can be transformed into another state phi. So when the Schmidt vector, okay, when the Schmidt vector for psi is majorized by the Schmidt vector for phi. Okay. Yeah. I'm sorry, I cannot hear you.
I think the majorization should be
You mean in our ordering? Let me see. No, this is correct. Yeah, this is correct ordering. Any question? Okay, so I just stated the theorems. Okay.
Is this a necessary and sufficient condition?
Yeah, if and only if. Yeah. So that's why this partial ordering is particularly useful in the classification. Yes. Thank you. Okay, so at least as far as you are concerned with pure bipartite quantum states, you have a clear-cut answer to this problem. Yes. Sorry, could you speak up a little bit? You're asking that, okay, so when psi's go to phi, phi cannot go to psi. No, yeah. Yeah, this is kind of irreversible, irreversible process, yeah.
If it is a unitary operation.
Oh, unit operation. Oh, which means that the psi and phi are the same, yeah. Okay, of course, yeah, that's a good question. So there might be a pair of states, so which can be transformed to each other in both ways. Yeah, there are such cases. And in that case, probably the operation is unitary, completely unitary. because unitary operation can be inverted. So usually separable operation is not unitary. But when it is unitary, so you have an inverse of the unitary operation. So then you can come back to the original state. Sorry, speak up, please. Map is reversible, yes? Yeah, in that case, lambda phi is modularized by lambda psi. That means a reversible process, yes. But in that case, so the two vectors are the same. Yeah, up to the permutation, yes. Okay, so this is one, okay. So this is one of the most beautiful theorem, results known in quantum information theory.
I have a question. So for a given vector, can you always find another vector which measures the given vector? Can you always find some vector? Is there some special vector?
Yeah.
You cannot find.
Right. So, for instance, good question. So, so here I have an example of the vectors, and the 1, 0, 0, 0, the rightmost vector is kind of strongest vector, so which can modularize any vector.
Which means that you cannot find any separable operation.
Okay, so given any quantum states, so any quantum states can be modularized by separable operation into this form. Yeah, into the 1, 0, 0, 0 vector.
There is no separable operation on the last vector.
Oh, yeah. The last vector, so the rightmost vector cannot be transformed into another quantum states by separable operation. Yeah. Okay, I will show you that, so yeah, this is kind of annoying notation. So here, so we order quantum states from the left to the right, and the left state can be modularized to the right state. But actually, the amount of quantum entanglement of the quantum states is larger. So when the state is on the left side, yeah. So it means that quantum entanglement only decreases under separable operation. So I will introduce a measure of the quantum entanglement using this order. Okay. So now, we have a clear-cut answer. Okay. So his characterization. So his theorem is very. So this is very strong result, because if you look at the Schmidt vectors, then the ordering of the Schmidt vector is a necessary and sufficient condition to answer to this question. But actually in practice, so computing the Schmidt vector is not so easy, especially so when the dimension of the Hilbert space becomes larger. So we probably want to, this is kind of, we have to compromise that we just introduce some measure, and which is easily which is computable, and it also gives us some ordering. So we want to quantify quantified order. Of course, when you can compute the Schmidt vector exactly, then you can answer. So you can answer to the ordering for the quantum states. But the computing Schmidt vector is not so easy. So we want to introduce more convenient measure, so which gives us some information of the order. So namely, so the basic idea is that, so this is again a space of, now I always consider the pure bipartite states. And Okay, so now I have psi and phi, and so we have LOCC or SEP, whatever it is. So then, so to quantify the order, so it would be very convenient to introduce some function. So function on this space. So this function preserves the order in the following sense. Okay, it is a kind of height function on this space, and if you have some nice function such that, so when the value of f on psi is larger than that's of phi, then the psi can be converted into phi. So now I'd like to find such a function. So namely, okay, so if x, so we want to find some function such that when x is modularized by y, then f of x is greater or equal to f of y. So we want to find such a function. But okay, so this is, okay. So such a function does not give you the complete ordering. We lost some informations. Okay? So namely, so when x is modularized by y, then f of x is greater than f of y. But the converse is not true. So when fx is greater than f of y, it does not mean that it does not necessarily mean that x is modulated by y. Okay? So this is a bit tricky point. Okay, so yeah, to my best knowledge, okay, I don't know any concrete example such that the converse is true. So the converse is not, I don't know there exists such a function. Okay, converse. Okay, let me emphasize this one more time. Okay, so basically, so we want to have, okay, this is called sure concave function. So we want to find sure concave function such that, so when x is modularized by y, then fx is greater than f of y. So this, okay, it does not mean that, okay, if f of x is greater than f of y, it does not necessarily mean x is modularized by y, but it means y is not modularized by x. Yes?
And B is is that exactly because this is a partial ordering, right?
This is partial ordering, yes.
Is it just, the
Not
fact that
complete
this is
ordering.
just a partial ordering means that you cannot conclude the vice versa.
Right. If you can find a complete ordering for the quantum states, the converse becomes true. But we know that there is no complete ordering on quantum states. So that's why we cannot find such a nice function. Okay, so 5 minutes. Okay, thanks. Okay, so maybe I should finish this point. And okay. Yeah, in the next lecture, I'd like to introduce some sure concave function satisfying these properties, and I'd like to talk about how it is useful in quantum information problems. Okay, I still have 5 minutes. Okay, so let me quickly give you the information measures. So this is called quantum information measure, or entanglement measure. Yeah, actually, yeah. What I'm talking about is actually quantum entanglement measure. So now we want to find a nice function, so which preserves a partial order. And okay, to define such a measures, okay, there are a few approaches. So one is just find, yeah, try and error, and you find some nice functions. But the other approach is kind of axiomatic. So you just assume a set of axioms. So in the axiomatic approach, so of course you want to impose the monotonicity of the function. By the way, can you read this? Okay, is it too small? Okay, so then, okay, when psi can be transformed into phi by LCC, then f of, okay, I will write the density matrix for psi as rho psi, and then f of rho psi is greater than f of rho phi. So this is the monotonicity axiom. And secondly, so you impose this condition. So this is the vanishing for separable states. So when psi is separable, then so we require that the function f vanishes. So this is just a kind of the origin, setting the origin of the function. So the separable state have zero value or in the function f. So this is the second requirement, and the third requirement is convexity. Okay, we require that the function f has convexity of this form. Okay, if f has convexity, then so you can draw some nice implications mathematically. So this is one input for the entanglement measure. And actually there are several entanglement measures. And let me give you one. So one example is that the relative entropy. I would say I can construct many nice measures from relative entropy. So relative entropy is, roughly speaking, is a distance. So distance between quantum states. So namely, so you have a space, of quantum states. I write it as a script S, and then so you can measure their distance using. Let me change the notation. So each point is represented by rho and sigma. These are density matrix. Then you can define the relative entropy between these two density matrices. And the reason why I say this is roughly distance is that it's not distance. So it's roughly distance, but it does not satisfy the axiom of distance. So the definition of the relative entropy is as follows. So it is defined using the two density matrix as follows. So this is the definition of the relative entropy, and So there are many nice properties of the relative entropy. So should I finish? Okay, give me 1 minute. Okay, so nice thing is that, okay, relative entropy satisfies monotonicity. Namely, so suppose lambda is LOCC or separable operation. So then, after the local operation, the relative entropy decreases. So lambda is LOCC over SEP. And okay, very roughly speaking, okay. Oh, sorry, this is too big. So first, so you have space. Okay, you have two density matrix, rho and sigma. Then after LOCC, so their distance becomes smaller. So they becomes closer and closer. So this is one nice properties of relative entropy. And I will, tomorrow, so I will construct the entanglement measure from the relative entropy. Okay, thank you very much. Oh, you are saying that so okay. So basically, yeah, rho and sigmas are usually the reduced density matrix. Only for subsystem, yeah. Okay, but of course, okay. So are you asking the definition itself, or okay, relative entropy can be defined for any two density matrix? Okay, here rho and sigma are arbitrary density matrix. Okay, say you can have a total density matrix. Oh yeah, great, yeah. I imagine that your system is bipartite. Yes. Okay, here so rho and sigmas are total density matrix. Total density, yes. Any question?
So when so can we go back to Nielsen's theorem?
Nielsen theorem, okay.
Oh, so how important is that our states are pure? Because the ordering means that the entropy decreased during the process, which is very strange from view of thermodynamics.
Sorry, so you think that this is strange?
Because the ordering means that the entropy decreased.
No, entropy always decreases.
Oh.
Well, maybe it's just a convention, so you can flip
Okay.
the sign. But yeah, usually entropy decreases. It's the definition of entropy. Okay. Yeah, if you like, yeah, you can flip the sign and define new entropy, satisfying this, the opposite relation.
Okay.
Yeah. Okay, that's why I say that this ordering is a bit annoying, because, okay, now, so when psi is modularized by phi, the entropy decreases, not increases. So, yeah, this is just convention. If you like, you can flip the direction of the, how can I call the order? Yeah, and you can define such a new ordering, if you like. Yeah, but it's just a definition.
Okay.
All right, so we are getting late, so we'll have again question and answer session in this afternoon. So let's quit this session. Thank you.